This is M63, which is evidence for global warming. One thing I forgot to mention before Module 62, when we started Chapter 19, was reading the opening case. So this opening case is interesting. It's about sea turtles and organisms. Some amphibians are like this too, where if temperatures change, so they're basically their sex isn't determined by X and Y chromosomes. They're determined by temperature as the egg develops. And so with an increase or decrease in temperature of the oceans, it can cause sea turtles or other amphibians to basically grow into more female versus male. So with this, they noticed that the female population in some areas has increased to 99%. So if it's 99% female, that's not a very good ratio for continuing that species. So so they're kind of delving into this and trying to figure out exactly, how this applies to their species continuing. Some places we see the opposite effect. So we're not sure if sea turtles will be migrating to different areas to develop, or if they continue to nest in the same areas, then we're going to see a sharp decrease in their population if we have really far numbers that are really far off as far as the ratio between male and female. So I forgot to mention that, but just make sure that you read that opening case. All right, so moving on to M63. So know what the IPCC is. So it's an organization that is basically looking at how global warming is occurring, maybe what global warming entails, studying the effects of global warming or the anthropogenic effects of global warming, and kind of trying to tie it all together. So that's kind of what the IPCC is about. And then moving over to page 695. If we look at this overall trend of CO2, we can see that the overall CO2 concentrations are rising. And then what it looks at are what these little tiny zigzag lines are across this blue, which is kind of the overall trend. So if we look at the monthly averages, the reason that they change is because of seasons. So if you think about it, CO2 in the winter versus summer is much different. So in the spring, like now when everything's growing, CO2 concentrations are going to be taken in by a lot of photosynthesis that's occurring. But in the wintertime or in the fall, when things are not photosynthesizing as much, then CO2 concentrations are going to increase. So throughout the year, you'll see little increase and decrease in CO2. But overall, if we look at the past, 60 years, 70 years, we see a trend of rising. And so this is just short term. So looking at the short term aspect here. And then we go back and we can look 500,000 years and kind of see what the concentrations were like. We'll talk about that in a minute. But you can see definitely that's a big overall difference in between 1954 and today. And so definitely overall the trend is going up. And then if we look at CO2 emissions in the world, 20% of the world lives in developed countries, but 75% of the CO2 emissions are coming from those people. So those people are polluting a lot. And basically it's in the form of fossil fuel use is pretty much where that CO2 is coming from. And looking down here at this graph, so what you need to understand, or this figure, what you need to understand down here is that if we look at how much CO2 is being emitted per country, China far outpasses all the other countries. So US is number 2 and then so on down the line. So if you look at just that, it looks like China has a big problem and they need to take care of it. But if you think about why, so why is China emitting so much CO2? Well, China has a lot of people. And so if we look at per capita, notice how China goes from the biggest emitter to way down the line behind Iran and above India. So a big difference there. And so United States stays at number 2 both times. So looking at this, United States per capita, we are the biggest emitters of CO2 per capita. Well, not per capita, but if we look at how much we emit and then see the difference between how much we emit and per capita, you can kind of assume or speculate that U.S. is emitting a lot more CO2 and contributing a lot more to the CO2 emissions or CO2 levels in the atmosphere than any other country. So that is not a good thing. If, let's say, a lot of these countries like China, India, those are developing countries. So what if they are down here on the list. So what if they all become very developed, very industrialized, and want to live like Americans? That would be an extremely bad thing because China already emits a lot of CO2. So to move up from here to here, that would be pretty dramatic increase of CO2 into the atmosphere every year. And so that is definitely something that would not be good. All right, so moving over to this side. If we look at this figure, what it's showing is global increases in temperatures. So if we look at global increase in temperatures, it's risen about 1.1 degrees from 1880 to 2017. So that is not equal, though. So it's not everywhere in the world has increased 1.1 degrees. So some places have actually decreased. So that's kind of what this is showing. It shows negative would be it's decreasing, and then obviously over here it's increasing. So looking at that, where is the majority of the increase occurring? Well, it's occurring in the north. So the northern hemisphere is experiencing a lot more global warming, in a sense, than the southern hemisphere. And areas in Antarctica, it's look at it, it's negative numbers, and so it's actually decreased a little bit. And this has a lot to do with albedo, sea ice, for example, in the northern hemisphere versus the southern hemisphere. But definitely, worldwide, we've seen an increase. If we look at all the areas worldwide, it's about 1.1 degrees, which doesn't seem like a lot, but it's actually a really, really big deal. And it has a lot to do with the sea ice. So if we look at the northern hemisphere, I just put it here on this, but northern hemisphere, it's increasing in temperature, Antarctica decreasing, but overall, it's risen on Earth. And then down here, it's we measure the temperature for the last 500,000 years. The way that we do this, because we weren't taking measurements for the last 500,000 years, but it requires indirect methods. So indirect methods, there's two. There's looking at species and how they change, maybe their diversity, maybe their types, where they're living. Those things can all give us clues and indicators as to what type of climate. And then also looking at ice cores. So ice cores are basically, they take these, most of them are from Antarctica. We take a lot of them from there. Greenland, we do some ice core data from Greenland as well. But what they do is they, over time, so areas towards the North and South Pole, they don't have a lot of accumulation of snow, and the snow doesn't really, it kind of stays and packs down. And so the snow over time compacts into ice. And when snow falls, it traps the gases that were present at the time. And so what we can do, and particulate matter too. And so what we can do is we can take the ice core, we can drill down, and the deeper you go, the older it is. And so we can extract that ice core and we can melt it down, and we can measure the amount of gases that were present. We can measure the types and amounts of particulates that were in the atmosphere. And we can figure out temperature based on that, and also looking at species that are fossilized from the ocean. So we can take all this information and we can calculate the amount of CO2 that was in the atmosphere, how much temperature fluctuations there may be. We can also see if there is melting occurring on that ice sheet or not. So there's quite a bit of information, but those are all indirect. So we didn't directly take those measurements, but we are applying what we know to what we see. So some of these indirect methods, looking at the species, there's foraminifera, and these are really tiny organisms, and there's different types, and different types like different temperatures. So different types will be in different parts of the ocean or different parts of the world depending on temperature. And so if we see them, we can do a count. We can date the rocks, so using radiometric dating to figure out how old the rocks are. And then we can see what types of foraminifera there are, and we know what temperatures they prefer. So we know that that ocean would have to be at that time that certain temperature. And so that's how we would look at species composition. And then if we look at the actual ice core data, what they look at is a ratio of oxygen 16 versus oxygen 18. And oxygen 16 I put on here, it's more abundant when it's colder temperatures versus the oxygen 18, which is more abundant during warmer climates. And so we can look at that ratio and we can determine the temperature based on that. And so that's from the ice core. And we have data back 500,000 years. So quite a bit of data. And this is what the ice cores look like. We'll look at it next week. I have a lab that will look at some ice cores that I've made. But you can kind of see how the scientists look at these and what they kind of look like. So when we look at what's in the atmosphere, CO2 isn't the only contributor to increase in temperature. So there's other causes in the past because there were times where the CO2 levels were much lower, but we had much warmer temperatures. And so other things in the past, Earth's orbit. So Earth's orbit isn't always exactly the same year to year. And so it does fluctuate. Same with the tilt. So right now it's 23.5 degrees tilt. It hasn't always been that way. And the Earth is a little bit wobbly. And the moon helps us stabilize the Earth in orbit. But the moon hasn't always been in the same position either. And so the moon is actually getting farther away from us every year. So that does affect the Earth's tilt and the wobble of the Earth. So those things can affect climate. And then also the position of the sun. So the position of the sun also fluctuates slightly. It's not a lot. A few thousand miles in space isn't very much. But it's enough to throw the climate off a little bit. And then also the sun, solar flares, things like that can affect climate here on Earth. And so those are things that can affect it without greenhouse gases. So it's not always greenhouse gases. And then if we look at this is showing the CO2 concentrations. So if you look at this is using ice core data. So we look back 500,000 years. It's kind of a regular kind of heartbeat if you look at it. But then look at what happened since basically the Industrial Revolution. It has skyrocketed. So over here, just completely shot up. So in the past 400,000 years, CO2 levels were never above 300 parts per million. Well, right now, they're currently over 400 parts per million. That is really significant. And when we look at the time frame of that, it has a lot to do with the Industrial Revolution, which is when we started burning fossil fuels. So there's other levels too that rise. So it's not just CO2, but this shows everything, or not everything, but the other greenhouse gases, the main ones. So methane, we can see a big spike in methane. We can see a big spike in carbon dioxide here, what we just looked at, and then nitrous oxide. So everything is rising, everything is spiking. So it's not just. Actually, this is supposed to say methane. So we already talked about CO2. But methane and nitrous oxide are also increasing. So make sure you note that on your sticky notes. All right, so scientists, looking at all this data, scientists have concluded that it's not just solar radiation that is causing, or it's not solar radiation that's causing global warming, but it has a lot to do with the increase in CO2, and that would be mostly caused by man. So make sure you read this section really closely. There's a lot of information. I couldn't really summarize it on a sticky note, but understand how scientists came to this conclusion. So it's found within this section, and like I said, it was too much to put on a sticky note, but just read through it and understand how they came to the conclusion that it's probably not solar radiation fluctuations, but it's increase in CO2. And so it has to do with the looking at the polar fluctuations and how they don't fluctuate with seasons. They fluctuate with CO2 concentrations. And then here's a graph. I'm sure this is kind of really a popular graph that pops up all the time. But it's showing CO2 concentrations and temperature change. And notice how they're pretty well correlated. So over the last 500,000 years, we can see that there's a pretty good correlation between CO2 levels and temperature change. And then if we look at the ice cores help uncover the past. Climate models help us predict the future. So they look at a bunch of climate models, and what they do is they put together things that have happened in the past with data that we have actually collected, and then they run the model into the future, which the future would be today. And the climate models predict accurately what's happening today. So that's how they kind of test these climate models to make sure that they are accurate. And so we can have these and use these to help us predict future. And so that's how they come up with the projections of sea levels will rise, or ocean or atmospheric temperatures are supposed to rise up to 4 degrees Celsius. So that's how they come up with that stuff. And then some areas may receive more or less precipitation. So it's not just everything's going to be a drought and hot. Climate fluctuates, and so some places might receive more precipitation than others, or than they used to. And then we get to this section on feedbacks. Well, actually, this part right here. So just kind of look this over, but it's showing, it's climate models, and it's showing low increase, moderate increase, and high increase in CO2. The high increase in CO2 looks pretty scary to me. I don't know about you guys, but I would go for let's do some renewable resources and lower our CO2 concentrations, because it's already hot enough here in Redding. So anyways, that's just showing kind of some climate models and predictions on increases, different amounts of increases in CO2 and what would occur. So then if we look down here, so there's positive and negative feedback. So just a reminder, a positive feedback doesn't mean good. I mean, it doesn't necessarily mean good. So a positive feedback means that things continue to get worse and worse and worse. So it's actually kind of a negative thing. But a positive feedback, something happens and it causes kind of an escalation of the problem. And so here's some examples of positive feedback. So the soil contains 2 times the amount of CO2 than the atmosphere does. So if we increase temperature, what happens is this leads to an increase in decomposition of the material that's in the soil. And decomposition by decomposers creates more CO2. And so that would be kind of a escalation of the problem. So that's a positive feedback. And then negative feedback, so I'm going to skip this little pink one for a minute. So negative feedbacks would be increasing in CO2 causes plant growth. So the plants take in CO2. So that's good, right? So plants grow bigger, better with more CO2. So that could be beneficial. But there is a limit to that. So there's only so much water available, so eventually, and only so much nutrients. So eventually it kind of stagnates. So it's not going to continue to get just big, huge plants. And then, so that's kind of beneficial. But then something that's not beneficial, we've got CO2 levels rising, so the oceans store more. Well, that's a good thing. So that's negative feedback, because the oceans are taking in more CO2 to combat the CO2 that's in the atmosphere. But what the problem with that is, and why it's not beneficial, is that it decreases the pH. And so that creates ocean acidification. So the oceans become more acidic. So shelled organisms, corals, they aren't able to build their shells very effectively. Their shells actually dissolve. It may lead to coral bleaching. So that would not be beneficial. Even though the oceans are taking in more CO2, that is not a benefit. We don't want our marine organisms dying because the oceans are taking in more CO2. So that would be negative. Negative feedback, because it's not negative. That's not the reason. But a negative feedback is when the problem kind of solves itself in a way. So something escalates, but then it brings it back into stabilization. All right, so moving over here. This is a positive feedback. I guess I should have talked about it with positive. But Arctic permafrost melting, so that produces methane, because when it melts, all of that tundra kind of just sits there and stagnates like a bog or a marsh. and that has low oxygen, and so that creates methane into the atmosphere. So that would be listed as a positive feedback. All right, and then the last thing, all systems are extremely interconnected. So the problem lies with trying to figure out, is it all human cause? Is it not human cause? All these feedbacks, everything is so interconnected that it's extremely difficult to figure out exactly what is occurring and how everything is tied together. And so a lot of people, I think, jump on that. And that's where we get a lot of the skepticism of global warming, is because people aren't quite sure, and we're not quite sure. We're learning about it. It's like having an experiment with 100, thousands of different variables. Well, it's going to be really hard to figure out exactly what's occurring and what's causing the outcome. So that's kind of where we're at. And the more we understand, the more we'll learn. But definitely to be overcautious would be good. And that's the end for M63.